Hi, my name is Hervé Paulino. I'll be presenting SAJ, a multi-user cooperative controller for mobile edge systems. Conjoint work with my students Nuno Coelho and Diogo Ribeiro from the Nova University of Lisbon in Portugal. So, the resource-rich environments that we currently have at the edge of the network provides opportunities for developing new types of applications. Here in this paper, we are particularly interested in collaborative control applications where users using their devices collaborate to control an asset, which can be an asset in the real world, such as stage lighting in a concert, have here on the left, or an object in a game. Here on the right, we have we control the pedals of the very well-known Pong game. To do this, we'll have to be able to aggregate tens to thousands of flows of events generated by the devices into a single flow to be handed out to the application. Furthermore, given that we are addressing highly volatile environments, we also have to adapt to the network conditions. They are ever-changing, and changes in the number of users, given that we want to allow for the dynamic entering and leaving of users in the system. So for that purpose, we propose SAJ, a distributed middleware to be deployed at edge networks that is able to aggregate a large amount of event flows into a single one to be handed out to the application, and also address dynamic discovery and connection, efficient network communication, and tolerance to churn. It also provides a generic framework for the programmers to tailor the system to the needs of the application by configuring several parameters such as data rate, the functions to be applied to the events that are generated by the device, and also the granularity of actions that we'll talk a little bit later. So the overall architecture of a SAJ deployment comprises a set of devices, which are the ones that users use to generate their flow events, and a set of servers, so one or more servers that will perform the aggregations. So if we have more than one server, this will be organized as a tree. So each device and each server can only connect to another server. The topmost server will be the one responsible for handing out the flow to the application. Note that devices may also act as servers, so to have which allows for deployments or more flexible architectures. So here we have two flows of data, one that flows upward, it's the flow of the events generated by the devices and that are being aggregated by the servers, and a flow of adaptation settings that flows downward from the servers to their subtree. So it may be generated by the source node or by one of the mid-level servers. So data sources are mobile devices or IoT devices, and they generate the flows of events by, for instance, moving the mobile device, or by pressing buttons, or by tilting the device, or by triggering some IoT sensor that will generate the events. These events are then transformed into actions. These actions are presented by an ID, a value, a weight, which indicates how many sources when taken into consideration when computing the value, and also a type, which can be continuous, so meaning that the values that the action can take are values in a continuous domain, for instance, motion captured by sensors, or discrete, which means that the values so the action takes values in a discrete domain. So for instance, example here is pressing a button. Regarding continuous actions, we assign them a time to live to avoid sending useless information repeatedly to the system. For instance, if we're tilting a device, if we tilt it for 2 or 3 or 4 seconds, we don't have to continuously send that information. We can just say that the device is tilting and have that assign a time to live to that information, meaning that the event will be valid in the system until the time to live expires, or a new event of the same type is generated by the same source. We also define the granularity of actions. For instance, tilting a device for a given application, tilt the device 30 degrees or 34 degrees may not be distinctive enough to produce a new event. So in that case, we do not send the new information. In fact, what we do is we divide the continuous domain into chunks, and only if an action event crosses the boundary of one of those chunks, it generates a new event. With this time to live and granularity, we're able to reduce network traffic usually. So the amount of information that flows is much lower, and also able to mask temporary disconnections, because if a device disconnects temporarily, the time to live may be enough to mask that disconnection. Regarding configuration settings messages, we want our system to be agnostic to the application. And so we have an initial message that indicates which is the identifier of the server to which the device is connecting, the description of the actions, the name and identifiers of the groups to choose from, if allowed. For instance, in the Pong game, the system may allow us to choose the team we want to play for, or simply assign us a team. And when so, that information also comes in this initial message. It also has a transmission period, which indicates, so what's the data rate the application is expecting. We can also define the maximum clients per server for load balancing purposes, but this is optional. When the system is running, adaptation messages will inform the nodes of changes in the transmission period, so in the data rate. Note that the data rate the application expecting is always the same, but the servers among themselves may adapt in order to, so given the current network conditions and the current number of users, adapt to be able to keep that data rate. So here we have the architecture of a source node. In Android, we have the graphical interface that allows the user to provide input. We also have the inputs that's provided by the sensors. Both are handed out to the system controller, who is the control center of the source. If the system controller decides that a new action event is to be generated, it sends it to data plane that will transmit it to the server. On the opposite direction, we have the flow of settings that is handed out to the system controller to adapt its internal state. In the server nodes, we have, so it's a little bit more complicated. We won't go into many details. We have here the network layer responsible for communication with the server's children and parents, and the data processing layer, which is responsible for aggregating the data flows, the event flows. So rapidly, we have here data flow. So the events are received by data receiver, are then passed out to the input connector that will relay them to the history and data streams handler. So the flow events is divided into batches. These batches are then passed to both the history model and then the data streams handler that we'll see in the next slide is responsible for the aggregation. The history is the model responsible for keeping the last event generated by each source, and if it's continuous, assigned it a time to live. Once the data streams handler aggregates the flows of events, this is then passed out to the parent connection handler that will transmit it to the server or the application if this is the topmost server. On the opposite direction, we have the settings that are passed to the settings handler that will adapt the server to the new settings and decide if a settings message is to be sent to the server sub-tree, and if so, this is handed out to the client's manager that has that responsibility. So regarding data processing handler, so it receives a batch of events. It splits this event into teams, into the groups. So here, for instance, if we have two groups, it will divide into groups that will be then passed to the next stage that will divide the events of each group in the actions defined for each of those groups. Here we have an example that we have two groups and two actions for each group. These are then processed by the programmer defined algorithm for each type of action. Once the results have been computed, the stream is merged into the flow events that will be passed upwards in the tree. So if for a given action, a given continuous action, there's no value in that in the current batch, the data streams handler will ask the history if there's still a valid value for that action from that source. If so, the value will be taken into consideration. If not, then so as explained in the paper, so actions will be taken care of for removing that client from the current population. So regarding the framework, so the framework provides methods to define all the configuration settings that we've talked before, such as the number and name of each group, the actions allowed for each group, the aggregation algorithm defined to process each of the actions, and also the adaptation algorithm that is used to adapt the transmission periods, among others. So we have here the example, so the signature of the method that has to be overridden to define an aggregation algorithm. So it receives a pair of values and the weight of each value, and must output a pair with the type of the output, and also the weight of all the elements that all the sources that were taken into consideration when computing this value. So the class algorithm provides a number of auxiliary methods, for instance, for discard duplicates, to ensure that in this collection there's only one element, the latest, for each source. It also allows for the aggregation algorithm to produce multiple results, which is not common but may happen, and also see how many, so what's the population, the current population, so the number of children of the subtree, and so on and so forth. Regarding the adaptation algorithm, it has two methods, one that is called when there's a need to increase the period, and one when the need to decrease. We have several implementations some inspired in network congestion protocols, such as additive increase, additive decrease, or qubit increase, multiple decrease, and also have Rebek, which is the one that we use by default, that is inspired in parallelism control in transactional memory. So the use cases that we present here are are games, cooperative games, where the users use the devices in the Pong to simply divide into two teams and control the paddle. Here on Arcanoid to also control the paddle and shoot, so activate power-ups that the game uses. So there are more details about this on the paper. Regarding evaluation, we performed evaluation in simulated environment as well as real environments. In the simulated environment, we're able to perform stress and scalability tests, also analyze the impact of the different adaptation algorithms, the processing overhead of the algorithms, also the impact of churn. In the real environments, we concentrated on energy consumption and also the impact of granularity. So there's an extensive evaluation on the paper. Here we'll only focus a couple of these items. So regarding scalability, here we have on the left a configuration with one server, 7,000 sources in the period of 1 second. And so here on red, we have the maximum output rate, and here on black, the minimum. And we'll see that a single server, which is a common computer, is able to keep the maximum base expected by the application. This is not always so. Here we have an example with also a single server, a little less sources in the period of 2,000 milliseconds, and we see that sometimes the server by itself struggles to keep this space, and sometimes it falls below the limit, although the adaptation algorithms try to keep it always between those two lines. When this happens, we can always scale horizontally with two servers. This is, you can see here the case, and with these two servers, so the system is able to maintain the data rate between the two lines, two desired lines. Regarding adaptation and churn, we try to condense it in a single slide. We have an experiment here with two populations. We'll focus just on one here on the 4,000 population. An experiment with 2,000. At the beginning, we have only 2,000 sources. Here, so around the 100 seconds, 2,000 more connect. This can be used to simulate, for instance, we had 4,000 sources and one of the servers goes down. So 2,000 move from that server that went down to the new server, to the other existing server. And then a little bit after 2,000 disconnect. So we have 2,000 and 4,000 and 2,000. We can see, so here is the input rate, and this is on the right, we have the output rate. And you can see here, looking at the output rate and also in the input, that at the beginning, when the 2,000 join, the server struggles a little bit because it has to accept a lot of connections. And at the same time, it has to adapt in order to keep the expected data rate. And so the data rate falls a little bit when it is able to recover. So accept all connections, it adapts, diminishing the transmission period in order to have the data rate close to the top as before. When 2,000 disconnect, so the data rate is now not enough, so the transmission period is not high enough to keep the expected pace, and the system readapts, and we'll see that it quickly recovers. Also have here a slide about energy consumption. So this is a mobile device. So here in the first bar, we have a mobile device that is not used as a server, only as a source. And you can see that 1 hour of use drains approximately 30% of the battery, which means that the device can be used for several hours as a mobile controller. So this is the application that we use to control the games. When it is also used as a server, we see an increase of almost double of the battery consumption. Here, used as a server, serving 20 clients, we have in fact doubled the battery consumption. So 20 clients is already a considerable number for a single mobile device. We usually will have less than this. but even when with 20, we can see that it can be used for a couple, so 3-4 hours before draining the battery completely. We can see that when we go from 20 to 50 clients, the increase is slight. So the big increase is when we add the extra layer of being a server. So conclusions. So SAJ is a distributed middleware capable of aggregating large amounts of data. It is directed to this particular case of cooperative control. And it offers a generic framework for building this kind of applications, so programming and setting up. So SAJ can accommodate hundreds of clients, thousands even, as we saw before. It scales it scales very good horizontally by adding more servers. And we see that the adaptation process manages to recover from performance drops. So whenever there's changes in the number of clients or even in network conditions. And the application that we developed for controlling games is a low power mobile application.